Imagine that you are trying to decide on a flavor of ice cream. You are only interested in 4 options: vanilla, strawberry, cookies and cream, and chocolate. You don't really care which one you get, and yet for that very reason you can't make up your mind. Finally, you reach into your pocket and pull out a pair of coins, a quarter and a penny. You flip both of them. Your idea is this: if both come up heads, you'll do vanilla. If both come up tails, you'll do chocolate. If the quarter is heads and the penny is tails, you'll do strawberry. And if the quarter is tails while the penny is heads, you'll do cookies and cream. Voila! Each outcome has an equal 1/4 or 25% chance. So you flip both coins, and wouldn't you know it, you get quarter heads and penny tails. Strawberry it is. From then on, your ice cream flavor decision-making troubles seem to be over. You only like 4 flavors, so every time you go to the ice cream shop, which is usually about once a week, you just flip both coins and go with the outcome. Out of a certain sentimentality, you always use the same pair of coins. You do this for about a year and flip your special coins a total of 60 times. You go a few extra times in there. But on the anniversary of your little discovery, you finally notice something odd. You've had strawberry and cookie cream ice cream significantly more often than you've had vanilla or chocolate. The ice cream shop owner happens to keep all past receipts, very convenient, so you ask him for the exact numbers. To your shock, you discover that out of 60 visits in the past year, you've only had vanilla 7 times and chocolate 8 times. On the other hand, you've had strawberry 22 times and cookie cream 23 times. In other words, you've had vanilla and chocolate only 1/4 of the time, but strawberry and cookie cream 3/4 of the time. It seems like your coin trick didn't work after all. But how could that be? It's an equal 25% chance. You think to yourself, perhaps the special coins you've been using are rigged. By some strange coincidence, you just happened to grab a pair of coins that are weighted in such a way as to give you skewed results. But wait, that doesn't make sense. In order for you to get vanilla or strawberry, for example, the quarter has to come up heads, right? Well, how many times did you get either vanilla or strawberry? 22 plus 7 equals 29 times, which is about 1/2 of 60. So you got quarter heads 50% of the time. And the same goes for the penny. In order to get, say, vanilla or cookie cream, the penny has to turn up heads. You got vanilla and cookie cream 23 plus 7 equals 30 times, which is exactly 1/2 of 60. So the individual coins can't be rigged. Each is 50-50 heads or tails. In fact, using the shopkeeper's records, you reconstruct a table of all your past coin throws. Sure enough, the quarters column shows 29 heads and 31 tails randomly distributed through the list. Meanwhile, the pennies column shows 31 heads and 29 tails, again randomly distributed. But when you stick the 2 columns together, they are miraculously coordinated, such that they are only both heads or both tails 25% of the time. Somehow, the game is rigged, not on the level of the individual coins, but on the level of both coins put together. This odd little Twilight Zone-like story serves to illustrate, in a simplified form, the chief idea behind a scientific experiment of extraordinary importance, the Bell test. Once again, it will be much easier to explain the Bell test abstracted from its historical context. For now, all that matters is that the Bell test is the actualization of a thought experiment initially proposed by Einstein and two colleagues, Podolsky and Rosen, in the 1930s. It was refined by the American physicist David Bohm in the 1950s, and was given a sharp mathematical and practical shape in the 1960s by Irish physicist John Stuart Bell. We will go over some of this history in a later section, but for now we need to lay some additional groundwork. In part 2 of this video, I characterized quantum theory as microscopically indeterministic. The antithesis of this position would be microscopic determinism, the idea that if we know everything there is to know about a particle, we can predict its behavior with perfect accuracy, as though it were a variable in an equation. Thus, the fact that quantum mechanics makes use of probabilities shows us, says the microscopic determinist, that quantum mechanics is missing something. It hasn't gone deep enough. It has not explained why the particles do this instead of that. It just says, only God knows. Well, let's explore some of the potential implications of this thesis of microscopic determinism. Perhaps we'll discover something that we can actually test. According to the thesis, any particle could be described in terms of its predetermined outcome in a given experiment. For instance, if some particle has a set of properties that guarantees it will be deflected spin up by Stern-Gerlach magnets oriented at 30 degrees, then we could rename that particle 30 degrees up. Alternatively, if a particle would be deflected down at 30 degrees, we could rename it 30 degrees down. And we could do this for any conceivable orientation, from 0 to 360 degrees, in the same way that we can plug any natural number into the term x plus 6 and get a definite output y. Thus, for any particle A, and given 3 particular measurement angles, we could give it the name A is 0 up or down, 120 up or down, 240 up or down. This simply means that if that particle were passed through a Stern-Gerlach test oriented at 0 degrees, then it would be deflected either up or down. And alternatively, if that particle were instead passed through a test oriented at 120 degrees, then it would be deflected either up or down, and alternatively, if that particle were instead passed through a test oriented at 240 degrees, then it would be deflected either up or down. Now, it doesn't actually matter how many hidden properties a given particle has, since the possible outcomes for any given measurement are limited to just up or down. Thus, for 3 different possible tests, there is a total of only 8 possible particle types that could give rise to those outcomes. In other words, given 3 possible test angles, say the 3 angles that are 120 degrees away from each other, we may sort the potentially infinite number of differently propertied particles into just 8 categories. Those that would go up at a 0 degree test, up at a 120 degree test, and up at a 240 degree test. Those that would go up at a 0 degree test, up at a 120 degree test, but down at a 240 degree test, and so on, like so. You can see the chart on the screen. Note that we are not talking about passing a particle through a gauntlet of successive tests, one after the other, like we were talking about earlier in the video. Right now, we are talking about hypothetical scenarios, where a particle is passed through one of the three options, but not the other two. For what we are interested in are simply the properties of the particle itself, which we are indirectly describing in terms of what those properties would lead the particle to do in different hypothetical scenarios. The particle type A3, for instance, includes all those particles whose properties are such that 1. If they passed through a test at 0 degrees, they would be deflected up. 2. If they were passed through a test at 120 degrees, they would be deflected down. And 3. If they were passed through a test at 240 degrees, they would be deflected up. What those properties are, we don't know, and we don't care. We only care that those properties inevitably lead to certain outcomes, with no room for spontaneity or probability. Now, our 8-particle table conceals a curious little property. We can reveal this property in the following way. First, couple the spin values for 0 degrees and 120 degrees, then for 120 degrees and 240 degrees, and finally for 240 degrees and 0 degrees. Now we have a second table full of pairs of spin values. Now note that there are two kinds of pairs, those with different spin values paired together, up-down or down-up, and those with the same spin values paired together, up-up, down-down. Let's make a third table where we replace the actual pairs with either the letter S for same or the letter D for different. Now, imagine that you have an endless stream of these 8 particle types. Further, imagine that we have a special device that can reveal each particle's predetermination for up or down along up to 2 orientations at once. By selecting random pairs of angles to reveal, we would generate a train of data like this. Assuming we are limited to the 8 particle types in the first table, we are therefore limited to the distribution of up and down in the second table, meaning we are limited to the distribution of same and different from the third table. In other words, given a very long line of spin data and a truly random distribution of the particle types, then as a matter of statistics, we should expect 12 out of 24, or 1/2 or 50% of the combinations to be the same versus different. Of course, there is an uneven distribution of letters. For 6 of the 8 rows, 3/4 of the time, D shows up 2/3 of the time, and S only 1/3 of the time. For the other 2 rows, 1/4 of the time, S shows up 3/3 of the time. Hence, 3/4 times 1/3 plus 1/4 times 3/3, or 1, equals 1/2 of the data will be the same spin. And if by some accident we only got particles from the middle rows, we could still expect no more than 1/3 to have the same spin value. And by the same token, we could at most only expect different spins 2/3 of the time, and more likely we would get them 1/2 of the time. The bounds for different spins are thus 1/2 and 2/3. So, if we are sampling from particles under a hidden variables model, we should expect 1/2 to 2/3 of our data to be different pairs, up-down or down-up. Well, that's all very interesting, but what good does that do us? We can only measure one axis of a particle at a time, because as soon as we measure it, the particle changes its state in response, and we have no way of knowing how this change affects the values of its hypothetical hidden variables. We can't perform two different tests on the same particle simultaneously, right? In 1935, Einstein and two colleagues, Podolsky and Rosen, often abbreviated to EPR, published a famous paper titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" There is a great deal I could say about this paper, but for our purposes, the important thing is that it identified a bizarre phenomenon predicted by quantum mechanics but hitherto unrecognized by its founders. Erwin Schrödinger would later dub this phenomenon entanglement. As we shall see, entanglement is trivially easy to explain under the traditional assumptions of microscopic determinism discussed at the end of Part 2. But under an indeterministic interpretation, it becomes far, far more difficult to explain. Entanglement usually results when a quantum particle, or a system of particles, decays or splits into two or more component parts. Before this decay, the quantum particle, or quantum system, has some amount of energy. Because of the conservation of energy, when that particle breaks apart, the energy is likewise split between its different parts. If we then measure one of those parts and find out its share of the energy, we can simply subtract this from the total energy of the original system, and thus deduce the energy that the other part must have. EPR originally discussed the entanglement of continuous quantities like position and momentum. Later, David Bohm applied their argument to the discrete quantities of spin, making the EPR point all the more striking. If we have, say, a pair of bonded atoms with a total spin value of 0, and we split the bond between those atoms, and we then measure one of the atoms as being spin up or +1, then we know, without having to measure, that the other atom must be spin down or -1. Thus, +1 plus -1 equals 0. This phenomenon of entanglement provides us with a natural way to analyze hypothetical scenarios, because it is nature's way of generating identical twins. We can measure the spin of one particle and then measure simultaneously a different spin on its twin. Thus, we can find out two spins on the same particle, or rather, we can test what a single particle would do in two separate situations simultaneously. The hard part isn't necessarily generating entangled particles, since all you really have to do is split a quantum system. The hard part is generating entangled beams of particles that you can control and reliably measure. But if you can manage to generate two entangled beams of particles, and you measure the spins in each beam, you will find that whenever the particle in one beam is spin up, its entangled partner in the other beam is spin down, and vice versa. We'll discuss the methods of doing such a test in a later section. Before that, there is one more thing we need to discuss. Imagine a quantum system with a spin value of 0. It splits into two parts, A and B. These two parts then fly through two separate Stern-Gerlach apparatuses. We find that A was deflected up, giving it a spin value of +1. We therefore already know that B will be spin down if we measure it at that same angle. But if it is true that the spin values of A and B were not predetermined before measurement, but rather A decided to become spin up as a result of being measured, swiveling around in a spontaneous way or something like that, then how did B know to compensate for A by likewise swiveling around to be spin down? It must be that some sort of signal or influence passed from A to B at the very moment of A's measurement, which allowed for them to coordinate their respective choices. But what if A and B were measured simultaneously? And what if they were measured, say, a light year apart, or even a light minute or a light second apart? A signal could never get from A to B in time unless it traveled instantaneously. In other words, it would have to travel faster than the speed of light. So it would appear that there is an additional kink in the indeterministic approach. It cannot explain the coordination of spatially separated particles without resorting to the concept of non-locality. For an event to be local means it obeys the speed limit of light. From every point in space, a cone of light is projected into the future, expanding at the speed of light, and whatever happens at that point in space can only be felt, seen, or heard at another point at a rate less than or equal to the speed of light, the expansion of that cone. Thus, under Einstein's theories of relativity, the universe is local. It takes time for an event at one end of the universe to finally ripple out and have an effect upon the other. Thus, locality is really more about the rate of cause and effect, which must propagate through space-time by means of local interactions. Space-time is effectively defined by the fact that nothing can traverse it at a rate faster than the speed of light. To put it another way, under locality, things cannot interact without touching, that is, without coming into physical contact in space-time and exchanging energy. It was John Bell who made this consequence of the EPR argument clear. Insofar as quantum mechanics is indeterministic, it is also non-local. This is what I was getting at with my terms microscopic indeterminism and macroscopic determinism. There is order in the universe. There are laws of energy conservation that need to be fulfilled. How are they to be fulfilled? Traditionally, we say they are fulfilled through the action of local causes. Particles go where they were pushed by a local cause. Something came into contact with them, exchanged energy, and caused them to go in this or that direction. But what if it turns out that this sort of local cause and effect does not hold at the microscopic level? How then do we account for the determinism that we see at our macroscopic level? For instance, the regularity of the wave patterns seen in diffraction experiments, or the reliability of Malice's law. We can only account for these by saying that a different kind of cause-effect relationship holds among the microscopic parts that make up the macroscopic wholes, namely, a non-local cause and effect. It is not enough to say that particles swerve spontaneously or make choices or however else we might characterize their indeterministic behavior. It must be that this swerving and choosing harmonizes at a higher level, and this harmony is, as it were, enforced by non-local causation, though this enforcement must be of a kind such that the very word enforcement is a misleading description of it. "Enough talk," said John Bell one day. "Let's experiment." Although he himself did not perform the experiment that now bears his name, he first proposed it, and it has since been carried out with increasing precision and forcefulness. You can generate pairs of entangled photons by shining a laser through a crystal of lithium niobate. The laser will pass through normally. However, at relatively infrequent intervals, the crystal will split one of the photons in the beam into two lower energy photons with entangled properties. This process is called spontaneous parametric down conversion. This forms a pair of faint secondary beams branching off from the main beam. Each photon in one beam has an opposite polarization from its partner in the other beam. So, if we place a polarization filter in the way of one beam, and a photon in that beam passes through, then we can be certain that the corresponding photon in the other beam did not pass through. They are mirrors of each other. In some sense, they are reflections of one and the same photon. That is, until they pass through the polarizer, since the polarizer triggers a change in their properties. But before that, they are reflections of each other. However, for the purposes of explanation, it will be much less of a headache if we can use the Stern-Gerlach version of this setup. So instead of polarization filters, we have Stern-Gerlach magnets, and instead of a laser beam shooting through a crystal to produce entangled photons, we have a block of material radiating entangled pairs of electrons or of whole atoms. It is much more difficult to produce reliable beams of entangled particles instead of photons, and I freely confess I do not understand this process very well. I was originally going to just use the photon example, but it introduces some additional conceptual snags on an already difficult topic, so you'll just have to trust me on this one that they can, in fact, generate beams of entangled electrons or particles as well as beams of entangled photons. The point is, we have two streams of entangled particles. Imagine that one is going to the right and one is going to the left. On both the right and left, there are Stern-Gerlach apparatuses. Each one can be oriented at one of three possible angles: 0 degrees, 120 degrees, and 240 degrees. We could choose any three angles we like, technically, but these three angles will give us the most striking results in the experiment, as we will see later. So, let's say that the setup on the right is at 0 degrees, while the setup on the left is at 120 degrees. Further, let's say that the particle on the right is deflected up, while the particle on the left is deflected down. So, for the angle settings 0, 120, we got up-down, or different, for that one run of the experiment. Now, let's repeat this for thousands upon thousands of particles at different settings, generating a list of ups and downs. The question of the Bell test is this: what will be the distribution of different versus same over this list? As we saw, if the particles are predetermined, that is, if the thesis of microscopic determinism is correct, then the number of different pairs cannot be higher than 2/3 or 66% of the list, and realistically, it should be closer to just 50%, just as we would expect of a pair of normal coins. And yet, the results of the Bell test do not meet these expectations. When the three possible angles are 0, 120, and 240, then the number of different pairs is 3/4 or 75%, if not even higher. Let me be clear here. We have a pair of entangled particles. One particle flies to the right, and the other flies to the left. The right particle enters a Stern-Gerlach apparatus and is deflected either up or down. Because that particle has not been measured by a Stern-Gerlach apparatus before, from our perspective, it has a 50-50 chance of deflecting up or down. It is a fair coin flip. So the right particle has a 50% chance of being up or down, heads or tails. And the left particle, which also goes through its own Stern-Gerlach apparatus, likewise has a 50% chance of being up or down, heads or tails. And in both cases, this fact is totally independent of the apparatus's orientations. It doesn't matter what angle we put them at, they're going to be 50% on either side. What is not independent is only revealed when we put the two lists of ups and downs together. We then discover that, although each particle has a 50% chance of being up or down, regardless of the apparatus angle, yet the chance of the particles being up or down at the same time, same versus different, varies with the angle between the two apparatuses in accordance with the Stern-Gerlach version of Malice's law. Thus, when our three chosen angles are 0, 120, and 240, then the apparatuses can either be offset by 0 degrees or offset by 120 degrees. In the former case, the particles are different 100% of the time. In the latter case, the particles are different 75% of the time. And realistically, this should really be closer to 1/3 times 1 plus 2/3 times 3/4 equals 5/6 or 83%. But 75% is the lowest possible bound. In other words, the two entangled particles are not behaving like two particles passing through two spatially separated apparatuses. Rather, they are behaving like one quantum particle passing through two successive apparatuses, one after the other. They are behaving like one single unity. In other words, the Bell test does not just support the thesis of microscopic indeterminism, since each particle has a 50% chance of being up or down. Microscopic non-locality necessarily tags along as well, since together the particles have an inexplicably low chance of showing up both up or both down. Order arises out of chaos non-locally. The term entanglement was first coined by Erwin Schrödinger in his 1935 paper Discussion of Probability Relations Between Separated Systems. It was inspired by Einstein, Podolsky, and Rosen's famous paper earlier that year. He writes, quote, "When two systems, of which we know the states by their respective representatives, enter into temporary physical interaction due to known forces between them, and when, after a time of mutual influence, the systems separate again, then they can no longer be described in the same way as before, viz., by endowing each of them with a representative of their own. I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought." Unquote. We can imagine, for instance, two dead planets whirling through cold space. They come within proximity of each other, exercise gravitational influence on each other, and then finally separate, continuing on their respective journeys, but both are changed by the interaction. They do not necessarily end up with the same properties that they began with. Their properties got tangled up with each other as a result of the exchange of energy that constituted their interaction. Or, to use another image, they pooled their resources together when they came into contact, and upon separation they divvied those resources back out again. But they need not divvy the resources back out in exactly the same way as when they came in. Now, a scientist who is trying to keep track of these planets might assign a representative to each planet, that is, a mathematical object that stands for each planet and its respective properties. But upon the planet's interaction, their properties change, and so their representatives change too. But the promise of classical physics is that, so long as we know all the laws, forces, and energies involved in the interaction, we can keep track of each planet throughout the course of the entire interaction, maintaining the same representative for each planet, only changing the properties of those representatives as a continuous function of time. However, we have seen that this does not work in quantum physics. What you put in does not guarantee what you get out. Probabilities intervene. Thus, as far as the mathematics goes, you cannot assign a separate representative to each particle after the interaction because there is no way to know from the inputs and function alone what the output will be. You can only guess based on probabilities. Consequently, you are stuck with assigning one mathematical representative to the whole system until you have a chance to actually measure one or the other part of the system separately. Writes Schrödinger, quote, "By the interaction, the two representatives, or psi functions, have become entangled. To disentangle them, we must gather further information by experiment, although we knew as much as anybody could possibly know about all that happened in the interaction. After re-establishing one representative by observation, the other one can be inferred simultaneously." Schrödinger continues, "Another way of expressing the peculiar situation is, the best possible knowledge of a whole does not necessarily include the best possible knowledge of all its parts, even though they may be entirely separated from each other." Unquote. Note that Schrödinger only speaks of knowledge of the whole versus knowledge of the parts. He does not say that the two interacting particles thereby become a new whole. He says that any attempt to mathematically represent the system must treat the particles as a whole, since the behavior of the parts does not necessarily follow from their previous state plus the function. See again the uncertainty principle. The hope, of course, was that this mathematical makeshift would be replaced by a discovery of the real mechanism determining the particles, so that we could dispense with mere probabilities. Such hopes were dashed by the Bell test, which shows that the connection between the particles is not an artifact of our ignorance, but a real feature of the particles themselves, made necessary by the fact that the particles are themselves indeterministic, but the macroscopic universe is not. It is essential to understand that entanglement is not an exceptional event. Rather, entanglement is the rule. Local interactions between particles result in their non-local entanglement. This much is clear simply from the mathematics of quantum mechanics. What the Bell test proves is that this mathematical description is not a gloss over our ignorance of what's really going on under the hood. It is a description of what's going on under the hood all the time. It is not an isolated phenomenon. It is involved in virtually every quantum interaction. It pervades the universe. Atoms are entangled systems of particles. Molecules are entangled systems of atoms. It stands to reason, I think anyway, that macromolecules are entangled systems of molecules. Cells are entangled systems of macromolecules. Organisms are entangled systems of cells. Societies are entangled systems of organisms, and who knows how high it goes. The typical modern view, beginning with the scientific revolution, is that the microscopic world is wholly deterministic. Atoms and molecules, the building blocks of matter, are dead bodies, which only move because of external forces acting upon them. It is the deadness of matter, its perfect submission to these external forces, that makes it deterministic, and thus predictable, and thus an exact science. Matter follows a strict, unbroken law of cause and effect, and we are assured of this cause and effect because nothing like free will is involved. Matter is dead, and the forces of nature are undeviating. There is no freedom here, no spontaneity. If there were, so the thought goes, the universe would be chaos. The typical modern view, in other words, relies upon force and coercion for its certainty. It is based upon a metaphysics of violence. Yet, assuming that any of my previous arguments are convincing, it seems apparent that matter is not dead. It is alive and capable of spontaneous action. The spontaneity of this activity forces us to resort to probabilities instead of exact predictions. One starts to feel as though we are no longer engaging in traditional physics, but a kind of quantum zoology. And yet there is strict order in the universe. These little quantum animals, so unruly on their own, nevertheless obey laws. Or rather, a better way to put it is, they participate in the maintenance of greater wholes. Insofar as their activity is free, they are microscopically indeterministic. But insofar as this free activity nevertheless contributes by an iron law of averages to the maintenance of higher unities, it is macroscopically deterministic. Non-locality is the assurance that, although no individual part behaves deterministically, yet their aggregated behavior is deterministic, and thereby serves as a solid foundation for the existence of the being that is composed of them. The causative relationship that exists between such a whole and its parts is wholly unlike anything we are used to in science. It is not a relationship of coercion or force. It is a voluntary relationship, and yet somehow it is perfectly orderly and reliable. It is a kind of harmony or synchronicity between parts and wholes. You move your arm. You, of course, feel as though you chose to move your arm. But what does that even mean? The motion of the arm surely is due to the component parts of the arm, the muscles, and ultimately the muscle cells, and ultimately the particles that make up the muscle cells. According to the modern scientific view, the whole process of moving your arm is bottom up, and your experience of free will, of choosing to move your arm, is simply a byproduct of the same bottom-up causes. It is an illusion. You did not choose to move your arm. The parts of your arm were caused to move by complex forces ultimately acting at the quantum level and having a domino effect up to the macroscopic level of our awareness. That is the traditional mechanistic view. But this bottom-up model depends upon the quantum particles, or whatever is at the bottom of our system, being dead matter pushed around by perfectly predictable local causes. But we have shown that this is not how the quantum world actually works. The quantum world is not locally caused. It is non-locally caused. In other words, the whole acts downwards upon the particles which make it up. The form of the wave, the form of the arm, the form of a society of parts, is not merely an illusion, not merely an epiphenomenon. It is a real entity, and although it cannot be manifested materially without the cooperation of the particles, yet it can non-locally influence its constituents to bring itself into being and act as a unit within the world. A group of people bands together and forms a society. Is this society merely a sum of the individual members? Yet members might leave or join the society at will, and different members might fulfill different roles within the society's structure, and those members might sacrifice their own interests in favor of the abstracted interests of the whole society, acting in ways that cannot be accounted for if we only analyze the individuals themselves. There is a proverb, often attributed to Nietzsche, though unfortunately I cannot confirm the source. It runs, quote, "They who were seen dancing were thought insane by those who could not hear the music," unquote. And this dancing to the music might persist even at great distances. A devout Muslim sojourning in a Christian country will still practice their religion, and so too a devout Christian in a Muslim country. Yet this illustration can be explained in terms of local causes. The Christian maintains their Christianity not because of any mysterious non-local causes, but simply because their religion is imprinted upon them and acts locally upon them through their habits. This behavior is not truly coordinated with that of their fellow believers, nor with that of their loved ones. It is not as though, by some spooky miracle, a religious person might happen to choose to pray at the very moment their loved one back home decides to pray, so that, despite being apart and acting independently, they are in fact praying together, just as they would do every night before bed, before they were separated. It is not as though the music of their mutual love could synchronize them across vast distances like that. And even if that did happen, if such a thing like that happened, we would say it was a coincidence. Well, all I know is that at the quantum level, it is not coincidence, nor force, but a kind of synchronicity that rules. The participation of several particles in a greater whole entails that, even when separated by great distances, they are capable of acting as though they were still together as one whole. They can both still hear the same music. But before we get too carried away, we should note that this kind of coordination is extremely difficult to maintain for very long. When the local bonds are severed between two particles, and they are spatially separated from each other, they will become re-entangled with the first new particle or system of particles that they bump into. This includes measuring devices, anything that triggers an exchange of energy and causes the properties to be tangled up. This, by the way, is one of the chief obstacles, if not the chief obstacle, faced by those developing quantum computing.